Okay, so thanks everyone for joining today. It's our pleasure to have Professor Niao here from ETH Zurich. She is an associate professor there, where she leads ODI group, Optimization and Decision Intelligence group. She's also a co-director of ETH Max Planck Center for Learning Systems, and also a faculty member with ETH AI Center. Before ETH, she was assistant professor at UIUC from 2016 to 2020. She received her PhD in operations research from Georgia Tech. Her research interests lie broadly in large-scale optimization and reinforcement learning, with primary focus on theory and algorithmic aspects to design these systems in a trustworthy manner. Her research has received AI Stats Best Paper Award, NSF CRII Award, SNSF Starting Grant, and many more. She's also on the editorial boards of SIAM Journal on Optimization, Journal on Optimization Theory and Applications, and has also served on area chairs in NeurIPS, ICLR, ICML, and other top ML conferences. So it's our dear pleasure to have Niao here for the seminar today. And today she's going to talk about multi-agent RL applied to mean field regime. Thanks, Niao, for joining, and the floor is yours.
Great. Yeah. Thank you for having me, and also thank you everyone for attending the seminar. I'm very happy to present some of our recent work on mean field reinforcement learning, and I think this is of close relevance to this particular community, and hopefully you'll find it interesting. Okay, good. So let's get started. Okay, I guess I don't really have to, introduce reinforcement learning or emphasize its revolution in the past decade, as you already have heard a couple of talks on RL topics in the past few seminars. As you can see that clearly very soon this page will be running out of space given the fast evolution of this whole field. So to cut it short in this talk, I'm going to focus primarily on dynamic systems that involve many competitive agents. Okay, and this particularly, I think you can see that this could occur in a wide range of applications, such as like resource management, in autonomous driving, strategic games, and many others. So in such settings, agents try to learn policies that are self-interested in order to maximize its own rewards. And the goal here, unlike the cooperative settings, is to seek to compute some kind of equilibrium. Okay. And as we all know that there has been significant progress made in this direction in many structured settings, such as zero-sum or general-sum Markov games or Markov potential games. And many of these contributions are really made by, the organizers or speakers and many audience from this particular group, I think, yeah. So in this talk, I'm going to particularly focus on the case with many agent or the many agent setting. So applications involving many interacting decision makers are indeed everywhere, and this ranges from a broad applications from, say, societal applications like online bidding to engineering applications like smart grids or traffic management, all the way to the science of modeling, say, brain activities or animal herding effects. And the problem is also notoriously known to be very hard to solve, and the hardness comes from several folds, particularly three curses I listed here. So the first one is really the curse of multi-agency, as we know that as the number of agents increases, the size of state action space will scale exponentially, and this would then require expensive computation and memory cost. The second is the curse of tractability, as we know that even without state dynamics, just computing the Nash equilibrium for general sum games alone is already PPAD complete. And PPAD complete is conjectured to have no polynomial solutions. And lastly, the curse of independent learning. It has been recently proved that if agents play independently according to some no-regret learning, which is a natural assumption, I think, for rational behaviors in the online learning setting, then it has been shown that it is already computational, intractable for the agents to learn some weak notion of equilibrium in the 3-player Markov games. At this point, it seems that this problem is rather hopeless, right? It seems like really a dead end to solve many agent reinforcement learning. But as a researcher, as someone who is from a theory side, we all know that what to do if we meet a very hard problem or if a problem is too hard, right? We either just approximate the problem or we just impose more assumptions, right? This is what we'll see in this talk also. Right, in particular, in a series of recent work, we shown that it is indeed possible to break all these curses with a mean field games approximation. And let me elaborate a bit more, right? Let's consider an agent reinforcement learning or an agent dynamic game problem where each of those agents has its own state transition dynamics PI and its own reward function RI that depends on the entire state and action among all those agents. If we assume that all these agents share a common transition dynamics and common reward function, and if we net this number of agents n goes to infinity, then we can actually obtain an abstract simplification of the so-called mean field games, where now all these individual interactions among the agents can be reduced to just the interaction between a representative agent and the population, or the so-called mean field. Right, in the mean field game settings, then for a representative agent, the state transition dynamics and also the reward now depends on the mean field or the state action distribution, which we call this parameter or this notation mu here. I should mention that this mean field games was originally actually introduced roughly like 20 years ago by 2 independent groups. And since then has been extensively studied in many other fields, particularly, I think, in the continuous time, continuous space settings. In this talk, we're going to primarily focus on the discrete time, discrete space setting. So let me just formally describe what is this n-player dynamic game looks like, and also what are the corresponding solution concepts and how this connects to the mean field game solutions. So in the n-player dynamic games, we assume that there are n players, and here we consider the finite horizon settings with horizon length h, and the finite state action sets are S and A. And we assume that each agent aims to maximize its own reward RI, following this particular dynamics, where each agent then selects some policies based on their own state information SI. Okay. So as every agent aims to maximize its own reward, a natural solution concept here is, of course, the Nash equilibrium, right? Which says that basically at this Nash equilibrium, no agents has any incentive to unilaterally deviate from this policy. In other words, no agent can exploit over others by changing its policy alone, right? So particularly if we're given a policy vector pi star, and we call it an epsilon Nash equilibrium policy, if the maximal exploitability among all agents I is bounded by epsilon. This exploitability is defined by the difference between the value functions, defined by differences in the value function between the current policy pi star and the best response policy that agent I can possibly take, right? So this is the so-called exploitability. So if the exploitability is less than or equal to epsilon, then we call this epsilon Nash. Apparently, if epsilon is equal to 0, then this implies pi star is going to be a Nash equilibrium. Okay, here we consider Markov policies pi that for each of these timestamp h, this pi I can depend on different time, can vary in terms of different time h. And the value function is defined by the cumulative rewards over this horizon of length h of all your reward functions. Okay. So similarly, when we come to a finite horizon mean field games, the dynamics then basically follows through this was written down here, right? In this case, both the reward and transition dynamics then depend on some population distribution or the mean field mu. And similarly, we can define the mean field gain equilibrium as the policy such that no agent can basically improve, such as that it is optimal, right, with respect to the current mean field. In other words, basically no agent can improve over its value function by deviating from this policy pi, right? Here again, the value function is then concatenated the reward over this horizon length of h, where this reward function depends on mu, right? This mu is the population, right, that was induced by policy pi. And particularly, there's this notation gamma p that we denote as the population evolution operator, which shows how the mean field evolves over time under policy pi.
Can I
So
ask
of
one
course,
clarifying question?
sure, yeah. Feel free to jump in if you have any questions. Yeah, I am sure I will miss many details here. Yeah. Go ahead.
So I have one question about the policy space you are considering here. So policy space here is only dependent on the agent's representative agent state. Is there
Yes.
any reason it's not dependent on the mean field? Like, I mean, I'm sure this is a very more stronger notion of policy that you are only looking at your state, but will it make any difference if the policy also depends on the mean field?
I think that's a very good question, and indeed, I think one could also consider these more general policies that also depends on mean field. This will definitely increase the complexity of the problem, I think. The challenge though is that it's oftentimes very hard to track the mean field mu, right? Because this is essentially some distribution, which is infinite dimension, right?
Okay.
So I think numerically, I think also from computation perspective, it's much easier to just consider
Right.
just the state. But this, I'm not sure if this would be already sufficient among all these policy class that includes also the mean field into consideration. But that's a very good point. Yeah.
Got it. Thank you.
So, because later we'll see that this is going to provide some good approximation, hence just to be aligned with the dynamic setting here, right? We assume that in the dynamic game setting, like for every agent I, it can only observe, right, its current state as I. So the policy will then depend on just its own current policy as I, state, sorry. The policy will only depend on its own state as I, right? This would not depend on all these other states from the other agents, right? So this is sort of aligned
Right.
consideration for the policy. Okay.
Got it.
Good.
Thank you.
Thank you for the question. Yeah. As you can see that in the mean field game setting, where basically this is an infinite player setting, where we assume that all agents share the same common transition dynamics and rewards. In practice, of course, right, when we're given an arbitrary n agent dynamics, n is not going to be infinite. And also the agents may not share common transition dynamics or rewards, right? Without going into too much of mathematical details, we've shown that actually for any n-player dynamic games, we can actually explicitly construct some mean field game out from it by taking some symmetrization and lifting it to the infinite player continuum to define some mean field games. And particularly, say, for example, if you're giving some n-player games, as I denoted earlier with different transition dynamics P and Ri for each agent I, then we can define a mean field game with this following transition dynamics P and R by taking some symmetrization operator, composited with some extension operator, and then taking averaging over all the different agents, and we can obtain this particular mean field game. So at a high level, you can imagine that we started with some n-player game, which is defined on a tensor domain, And then we wanted to do some symmetrization operators to lift it to some state distribution, which is like defined on discrete points. And now we're going to just consider a Lipschitz extension to lift it into the continuous domain in the simplex set so that we can have a well-defined mean field gain. Okay, so this is just some high-level intuition. Okay, and the specific details of how this is constructed doesn't really matter, because later on you'll see that this mean field gain construction will not really be used for algorithmic purposes. It's just going to be used as a mere like proof strategy. So with this mean field gain kind of construction in mind, then this basically induces three fundamental questions that we would like to answer. First of all, we want to know how well does this mean field gain approximate the original n-agent reinforcement learning problem, right? Secondly, we want to know how easy it is to solve these mean field gains. In particularly, right, what are the computational and statistic complexities of solving mean field gains? And how can we design algorithms that realistically interact with large multi-agent systems rather than interacting with the mean field gains? And lastly, we want to see if it is possible to solve the problem or to solve the original reinforcement learning problem by just allowing n agents to learn independently without any coordination, right? So in the rest of the talk, I'm going to answer these questions one by one. And then I will wrap up with a concrete application on auctions where we see how we can piece all these together in order to see how things work actually in this application. And particularly here, I'm going to even take a step further to go beyond from learning problem to incentive design problems and see how we can leverage mean field gain approximation and also the tractability guarantees or benefits in order to solve this efficiently. Okay, so here's the outline of the talk, the rest of the talk, and I'll just quickly pause here in case there are any questions at this point, and happy to take it for now. Yeah. All right, good. Looks like we're clear. Good. So let's first dive into the approximation side. Okay, so the question is, how well does this mean field induced mean field gain approximation that we just constructed approximate the original n-agent gain? So in order to characterize goodness, right, we can use a natural notion, which is this exploitability, to characterize the goodness of the solution we get from mean field gains, right? Suppose we know how to solve the mean field gain exactly, and we get some equilibrium policy pi star, and we let all those n agents adopt this policy pi star. And then we see what's the maximal exploitability, right? If this maximal exploitability is less than or equal to epsilon, then that means this mean field gain provides an epsilon Nash equilibrium for the n-agent gain. So there actually has been a lot of existing work already, right, that considers the setting where agents are symmetric and considers the case when n goes to infinity. How does this mean field gain approximates the n-agent setting, right? Particularly, we know that when n goes to infinity, then the n-agent gain actually converts to the mean field gain, right? There has been actually a lot of other different variations of the mean field gain settings where people obtain similar asymptotic results. As I mentioned earlier in this talk, our focus is really the case where we have finite number of agents, finite horizon length h, and possibly heterogeneous agents. Okay. So here's one of our main results, right, where we're showing that if we just adopt this mean field gain equilibrium from the induced mean field gain approximation, then the exploitability, n-agent exploitability, can be bounded by this term here, right? So this looks a bit complicated. Let me just unpack it for you. So the first term here basically captures the effect of having only finite number of agents. As you can see that this term scales in the order of 1/square root of n, right? As n goes to infinity, then this term will diminish to 0. So you might notice that this actually has a very high dependence on this constant L. This constant L is the Lipschitz constant of the population evolution operator that I introduced earlier, right? That is the gamma p operator, which captures how your population, your mean field, evolves under policy pi. And if the Lipschitz constant is, say, less than or equal to 1, right, meaning that this is indeed a non-expansive operator, then this first term will only have very mild dependence on the horizon edge, right? The dependence will only be just a quadratic, right? In the case where this Lipschitz constants may be large, where say L greater than 1, then this is a case where the dynamics can easily lead to chaos, and you can then see that there is actually this exponential, possibly exponential dependence on L and H from this first term. Okay. So the second term actually captures the effect coming from the dynamic heterogeneity, right? If the dynamics are for different agents are different, right? We capture the maximum degree of difference by this quantity alpha. And this is this second term here, which has similar dependence in H and L as the first term. And the last term captures the effect coming from reward heterogeneity, where we use this quantity beta denotes the maximum degree of difference among different agents, which is similar defined as alpha. Okay, as you can see that the reward heterogeneity has a much minor effect on the overall approximation error, right? The dependence on effective horizon or horizon H is much smaller, right? This is just linear dependence on H. And here it could be potentially exponential dependence on H. So as you can see that if alpha and beta are equal to 0, this basically reduces to the exact symmetry case. Then we don't have this will diminish to 0, right? And as n goes to infinity, then the approximation error will converge to 0. So a key takeaway here. Yes, are there any questions? Okay, no, good. So a key takeaway here is that, as you can see, that this mean field approximation, it can be quite good if the underlying dynamics is stable in the sense that L is small, like less than 1 or less than or equal to 1, and it is robust to small violations of symmetry. If alpha and beta are small, then this bound will be small. Okay. So I just mentioned that in the exact symmetry case, then this gives the non-asymptotic bound of the mean field gain approximation, which scales in the order of 1/square root of n, and has a dependence of L to the power of H, which in the worst case could be exponential in H. And we actually shown that in the lower bound result that in fact, if you don't impose any additional assumption, this exponential dependence cannot really be avoided, right? This you can easily construct some finite horizon mean field games which admits unique equilibrium, but the exploitability will be very large unless n is exponentially large. I know whenever I give a talk on reinforcement learning, half the audience are interested in finite horizon, half the interest then will be interested in infinite horizon. So here we also had some result for infinite horizon mean field games, and the results are more or less similar, right? Suppose the population evolution operator is non-expansive in the discounted setting, then we can show that the approximation error again is bounded by this 1/square root of n term, up to a cubic dependence on the effective horizon, which is 1/1 minus gamma, that basically matches with the finite horizon setting. And if we don't have any of this non-expansiveness assumption on the evolution operator, then the exploitability can converge arbitrarily slowly in terms of dependence on n, right? So this result basically also hints that, right, in order to have good approximation, right, some of these assumptions like a non-expansiveness is sort of necessary. So that it basically summarizes about the approximation guarantees, and we see that indeed with mild asymmetry, right, we have good approximation.
So
the
next
question,
question.
yes. Sure.
So in the theorem which you have, there is terms S and A. Are they the state space and action space of a representative player, or if there is an n player agent, this is like a joint state and action space?
That's a very good question. So in our setting, we just assume that all agents, although their state and reward dynamics are different, but they select a state and action from the same set. Or you could also view this as the kind of the concatenation of all the state action space. Yes.
Okay, thank you.
Good point. Yeah. Good. So with this good approximation, right, we want to see also how easy it is to solve these mean field games. Particularly, let's say, if we assume that we know the underlying models, we know the transition dynamics and also the reward functions of your mean field games, right? How easy it is to solve these mean field games. We know that in the n-agent setting, this problem is PPAD complete, right? It's very hard to solve. What about the mean field games? In fact, this question has been partially answered already by many existing work. And a lot of this work actually assumes that, shows that if the underlying, right, this operator, relation evolution operator is contractive, then you can show that solving the mean field gains basically reduces to repeatedly solving some single agent reinforcement learning. So this can be done very efficiently, right? Or in other settings, it has been shown that if the reward in the final horizon mean field game settings has been shown that if the reward are monotone and if your transition dynamics doesn't depend on the mean field, then this also can be efficiently solved, okay? Recently, we try to kind of explore this a bit further to see, do we really need these structural assumptions, or what is going to be the complexity if we don't have them? So it turns out that rather pessimistically, that if we don't have any of these structural assumptions, if we just impose very basic assumptions like Lipschitzness of your dynamics P and your reward R, then the problem becomes very hard already. This we can show that is already PPAD complete. And note that these are minimal assumptions to even already guarantee existence of Nash equilibrium, right? So the Lipschitz continuity assumptions are really minimal here. So basically this result hinted that really there's a reason why people introduce these very strong assumptions, because without these structural assumptions, then solving mean field games is very hard, okay? So in practice, of course, we don't always know the model, and the reward function and the transition dynamics may not be known, right? So we have to generate data or have to sample trajectories by interacting with the mean field games in order to learn what is the underlying Nash equilibrium. So here, the next question I want to ask is, putting aside the computation cost, right? Is it statistically tractable to learn mean field games within, say, a given hypothesis class, right? So in other words, like how many samples are sufficient in order to learn an epsilon Nash equilibrium? So in the single agent setting, this sample efficiency basically boils down to the exploration challenge, right? And this has been widely studied by, I think, in the reinforcement learning theory community for, say, both the tabular settings or the function approximation settings, right? A lot of the existing results shown that the underlying basic sample complexity depend or is governed by some algebraic dimension of the underlying MDP under some function approximation, such as a Luder dimension or Bellman rank, which can be proved to be small under some, say, linear MDP settings or tabular settings. So one can intuitively think that for when we move to the mean field game settings, the exploration will become much more challenging, because the state dynamics and also the reward now depends on the mean field, which is an infinite dimensional, right, distribution there. So what will be the statistical efficiency there. Surprisingly, I think in our recent work, we've shown that actually learning this Nash equilibrium for mean field games is statistically tractable, or the sample complexity actually is only polynomial dependent on some intrinsic dimension. So here's kind of the result, right? So where we assume that we are given a model class M, which contains the true unknown model M star. So this is the kind of the minimum realizability assumptions that we see in a lot of the reinforcement learning theory literature. And we also assume that the transition dynamics and the reward are Lipschitz, okay? And we can show that it's possible to construct some model emulation algorithm that would be able to find some Nash equilibrium within only polynomial, with sample complexity that only depends only polynomially on the horizon H, also polynomially in the Lipschitz constants we see earlier in 1/epsilon, and in some intrinsic dimension, which we introduce as the so-called model-based eluder dimension. This is a generalization from the single agent setting to the mean field game setting. And this can be proved to be upper bounded by the size of the state action in the tabular setting, and is upper bounded by the feature dimension in the linear mean field game settings. So this kind of aligns with what we see in the single agent MDP setting. As you can see that in the special case where these Lipschitz constants are equal to 0, right? This basically means that the transition dynamics and the reward has no dependence on the mean field. This basically reduces it to the single agent setting, and this recovers what's known in the literature for single agent setting as well. So the takeaway message here is that I should also mention that this whole result, right, does not require any additional assumptions like monotonicity or tractability assumption, right? These are really just very minimal assumptions. And it turns out that statistically speaking, learning mean field games is much more tractable than the computational side.
I have one quick question. So maybe I missed
Sure.
something here, but you earlier said that the contractivity, some kind of contractivity assumption is required to make sure learning equilibrium is tractable here, but it seems there is no such assumption here. So am I missing something?
Yeah, there is no such assumption here because we only care about the statistic complexity, like the sample complexity. We don't care about computation complexity here. So in the algorithm, like it requires, some oracle assumptions, which then requires solving some, mean field game subroutines, and that can be computationally intractable still, yeah, without these additional assumptions, yeah.
Sounds good.
But
Yeah,
the whole point is if we are putting aside the computation cost, then if we just look at how many samples we need, then this is tractable. This is only polynomial dependence on the size of the problem. Yeah.
Sounds good. Thank you.
Cool. Yeah. Thanks for the clarification question. Yeah. Great. So now we have shown that this mean field gain gives us a good approximation and also a tractable approximation under some assumptions, right? In practice, of course, we cannot really implement the mean field games because this then requires to simulate infinite number of agents and also required us to have some centralized controller to broadcast the policies to individual agents in order to keep track of what is the population, right? So, and this is very unrealistic. So this then brings up to the next questions is that can we just leverage the N-agent simulator in order to learn the desired Nash equilibrium? And can we just allowing agents to play independently without any coordination to do that? So that is our goal, right? And of course, a natural algorithmic idea one can think of is basically to let each agent play policy updates or play like, say, for example, policy mirror descent algorithm, right? Here's a simple routine is basically at every iteration, we let every agent to learn its corresponding value functions like Q functions or value functions. And then we just based on this Q function or value functions to then update this policy purely based on its own observations on its own states, right? So this kind of is basically the independent polymer descent counterpart for the n-agent game, right? So that is basically a very generic algorithmic framework that we're going to consider, okay? So in the series work, we've shown that if we have these additional structure assumptions, as I mentioned earlier, then if we just let these n agents to run this polymer descent independently, it only requires polynomial in terms of 1 or epsilon sample complexity in order for the agents to converge to some epsilon Nash equilibrium up to the approximation error and the symmetrization bias. Okay, so this results holds in a number of different settings that we analyzed carefully. So the first setting is when we have the stationary mean field games with regularization. This is a case where we can show that the population evolution actually has this contractivity property. And another setting that's kind of new is the case where we consider static mean field games, where we don't have any state dynamics anymore, right? It's purely just a sort of a banded setting, but we assume that the reward function is monotone. We can show that again by just doing independent learning with mirror descent, the algorithm will converge to a epsilon Nash equilibrium. And more recently, we extend this further to just n-player dynamic games with monotone rewards and also with mu-independent dynamics. And we've shown that also independent learning can be achieved. And one thing I would like to particularly emphasize here is that we only use this whole mean field gain approximation more as a proof tool rather than as an algorithmic tool. Right, in the algorithm, we always just run an agent simulator, and we just observe an agent state action, right, transitions. We don't really just simulate mean field games or solve mean field games directly. Okay, we're really just using this as an abstraction, this abstraction as a proof to show the approximation error and to develop the bounds. So just to give you some flavor of what type of results one can expect in one of these special cases where, say, we don't have any state dynamics, right? We just have n agents, and each of them can take k possible actions, and the corresponding reward function will depend on the whole distribution of this action among all those n agents. Right, so we call this the static mean field games with banded feedback. And we've shown that in this case, if we have some monotonicity assumption on the reward, then the exploitability can be bounded by these two terms here, which then yields a polynomial dependence on the sample complexity. Okay, if the reward is further strongly monotone, then you can further improve the dependence in terms of n in this bound here. And these bounds are by no means optimal, right? There's still a lot of, I think, room to improve these bounds to some degree. Yeah. Good. So that is on the independent learning side. And now, next, I wanted to see how we can really just piece all this together to see how this mean field approximation works in some application. Okay. And particularly, I'm going to consider an even more challenging setting with incentive design for multi-agent systems rather than just learning multi-agent systems, right? The goal here is really that we wanted to be able to design some environment parameters such that these multiple players who are self-interest can reach to some desired equilibrium, right? Mathematically, basically, this then can be formulated into the following problem where we assume that we have n agents, right? They can repeatedly interact with some parameterized dynamic games, where these dynamic games parameterized by some parameter, say theta, environment parameter theta, right? And the goal then here is that we wanted to maximize some global function g, such that these policies pi 1, pi n form the Nash of the dynamic game given this particular parameter theta, right? We want to maximize over G theta over theta, right? We want to find the best mechanism that returns the optimal global function and gets the desired Nash equilibrium, okay? So one example of our interest is the case where this dynamic game basically is some multi-round auction problem. And naturally, the objective G there would be the revenue of the auctioneer. Okay? Of course, this also appears in many, many other applications like pricing on the smart grids or congestion control in traffic and many others. I think in the previous seminars, you also have seen a number of talks on this. So of course, we know that already given a parameter theta, right, solving this, finding this Nash anom is already hard, not to mention maximizing this additional global function, right, for any given theta. So now we're going to use our mean field gain tools, right? So we're going to just approximate this incentive design problem by approximating the dynamic gain with this mean field gain, okay? So instead here, we're going to just maximize global function, right? By trying to find the mean field gain Nash equilibrium, okay? And we've shown that similar as before, right, we can provide good approximation guarantees. Particularly, we can obtain both 1 over square root of n approximation bound, both in terms of exploitability and also in terms of the optimality of the hyperobjective G, right, the design objective G here. And this can be obtained both in the Lipschitz setting and also in this special auction, like multi-round auction setting, which actually is much more challenging than the standard like Lipschitz mean field game setting, because the underlying dynamics is no longer going to be Lipschitz. And this mean field gain approximation then admits, of course, very efficient Nash computation, right? As we shown earlier, right? We can just run iteratively Fokker-Planck and also Poisson-Mir descent, and then we can then gradually converge to a mean field gain equilibrium, right? But this is not end of the story, right? Because this basically says that for a given theta, we know how to compute the pi MFG, but in the end, we still want to maximize or optimize this global function, right? So we needed to be able to solve this hyper or optimize this hyper objective. And in a recent work, again, we shown that it's possible to actually apply the adjoint method, which was widely used also for bi-level optimization, to show that it's possible to actually back propagate all these n-agent, update rules in order to get a good, gradient estimate for the hyper objective. And then we can then just use this to we can then just based on this to just run this first order method on the outer, like the hyper objective, and solve this incentive design problem efficiently. And I should mention that actually the memory cost for this is also relatively low with this adjoint method. And this is the application we have in mind to solve this for the large scale batched auctions, where in this batched auctions application, at every round, the auctioneer can decide or can design a proportion of goods to sell to the top bidders. And then it can also design what is the payment for the goods. And the goal there then is to design this proportion and also the payment in order to maximize the revenue, okay? And we consider particularly these alpha and P that are parameterized by some residual neural networks, and in order to just solve the problem, okay? So in our experiments, we basically compared this first order method I mentioned based on this adjoint method, and compared it to just some other, like say, zero order methods by just doing some perturbation on your parameter and then trying to compute the Nash and take the difference of the function values in order to estimate the gradient. Right, we compare this first order method with a bunch of zero order method and also the first price baseline. And we can see that the method, the first order method that we proposed based on the mean field gain approximation actually performs much better than the other methods. So this is kind of something very positive that we can see from this particular application. But of course, we're also interested to look into many other applications that involve also more real world data sets. And if you have any good ideas, what could be good relevant application, feel free to just reach out to me or to the group. Yeah. So with that, I think it's also about time to conclude that I want to remind you that we started with these 3 fundamental courses of many agent reinforcement learning. And I hope I have convinced you that, this mean field gain approximation can be served as a very promising, solution to address many agent reinforcement learning, especially if there is only mild asymmetry among these agents. Right, this is promising both from the computational perspective or also from the more realistic independent learning perspective. Of course, in practice, if we are going to have applications which goes beyond this mild asymmetry assumption, then this mean field gain approximation will no longer be ideal, right? So in that cases, then we need to think about alternative approximation, more flexible frameworks to approximate the many agent reinforcement learning. And one kind of possible idea is to leverage, say, for example, multi-type mean field games where we can group different agents, right, that are similar to each other into the same type, and then we can have this more kind of generic multi-type, multi-population mean field games to do the approximation. And this could be something interesting to explore in the future, I think. With that, before I stop, I want to say that this presentation is really built on many collaborative work with a number of co-authors, and particularly my PhD student Batu, who is really the main drive behind many of these contributions. And he should get all the credits. And these are the related papers that I discussed today. And thank you very much for your attention, and I'm very happy to take your questions. Yeah.
Thanks, Niao, for the great talk. So let's now open the floor for discussion. So yeah, feel free to unmute yourself and ask any question for people on Zoom and at Berkeley.
Could I ask a question?
Yeah, please.
Okay, thank you. So I found the complexity results you presented in that table really interesting. I'm familiar with some of the authors who put some structure and they show kind of simpler complexity. And so I like that result. I guess my question is, yeah, this one. I'm familiar with some of the ones in the top. I guess my question is, sometimes when folks have gotten these kinds of PPAD complete results, they argue that we should be thinking about some kind of model besides Nash equilibrium. And so I guess my question is kind of, I wonder if you have any thoughts about that argument.
Yeah, that's a very good question. I think definitely the complexity is tied with what type of solution concepts we're looking at, right? Oftentimes, if computing Nash can be hard. That's why a lot of I think existing work tries to relax the solution the equilibrium definition, right? To consider, say, coarsely correlated equilibrium, or even some other weaker notion of equilibrium, or zero, right? Or stationary, like first order equilibrium or sort of things, right? And when you relax the solution concept, oftentimes, right, you can show possibly, right, this is no longer going to be very hard, right? So there is of course a trade-off between, what type of, strong notion of the solution versus the complexity. So there are also a lot of these other results as well out there, right? Particularly here, we look at the Nash equilibrium because I think it's the most natural one. And we do also have some other results for, say, in the not only in the game settings, but also in the, like, say, mean field control settings, right? The notion would not be Nash equilibrium, but some other, right? The global some other some other notions, right? And then the complexity will also be very different. So it really heavily depends on what type of solution concepts we're looking at. Yeah. So that's a very, very good point. Yeah.
Thanks. Any other questions? I have one question in the meantime about the incentive design part. So one thing which you showed this neural network module, which computes the gradient of hyperobjective. So are you assuming some kind of uniqueness assumption here that the mean field equilibrium will be unique?
Yeah, this is a very good point. Yes, that's a very sharp observation. Yes, we do assume uniqueness here. Already with uniqueness, I think it's not a trivial task to propagate in order to compute the gradient of the hyperobjective. Without the uniqueness, this will be much harder, right? Because this will be a much more challenging task. Yeah. So there are two reasons why we assume uniqueness. The other reason also is because in order for us to compute the Nash, as I mentioned earlier, right? Oftentimes we have to assume this monotonicity or contractivity, and that naturally basically requires some regularization on your mean field gains, and that would implicitly already imply some unique Nash. So going beyond the unique Nash or unique solutions for the sort of the lower level problem. So recently we had some work which is not for dynamic games, but more for generic, say, bi-level optimization, where we have lower level problem that is not necessarily going to be convex or strongly convex, and it might admit multiple, right, optimal solutions. And then there is a whole matter of how do you do minimal or minimal selection or equilibrium selection, right? Because then your hyperobjective will have to be adjusted to whether you wanted to consider, the best minimum or the worst minimum, right? There is the pessimistic formulation or there is an optimistic formulation for this impact problem or bi-level optimization problem. And that then requires this very, to solve this very difficult problem called minimal selection, where you wanted to find the minimum, the best minimum among a set of minimum, right? And this set may not necessarily even be convex, right? Because we don't have this strong convexity or uniqueness assumption. So in our recent work, we've shown that if we just impose or we just assume some mild, say, local PL growth conditions, then we can show that the minimal set, actually, it also applies to a lot of applications in neural networks, that the optimal set from the lower level problem actually forms some smooth manifold that is connected. Okay.
Got it.
And then you will be able to actually do this minimal selection over this manifold of minima very efficiently using some line-driven dynamics or some other tools. So there is actually a way to address the setting where the equilibrium or the minimum is not unique.
Quite cool. Quite cool. Thank you.
Actually, I also have a question. So I'm coming more from a physics field, so I'm not very, I can't very much, so I'm not sure if, so you asked for an application or if any other people have ideas for applications for multi-agent approximations. So I'm not sure if this is like a good idea because I'm not from this field very much, I'm more from a physics field. And in physics, I work on an experiment, which is, which we want to calibrate basically. And the experiment has different moving parts that has to be like paths have to be aligned in certain ways to optimize basically the experimental sensitivity. It's actually a dark matter experiment. And what I had to look a bit into is when I align for example, the antenna, one of the moving parts of the experiment. And as an environment, I have the basically some calibration metrics. I looked into using reinforcement learning to basically find an optimal position for the alignment of the antenna in the experiment. But there are more moving parts in the experiment, which all depend on each other. So I was wondering, how do you assess, or what do you think how feasible it would be to try to apply something like multi-agent reinforcement learning approximations like you just presented to a physical system where I have different moving parts which are basically can be understood as agents for this problem. So I think it's like a completely different field, but maybe there's some potential in it.
I mean, there is definitely a lot of connections. I mean, the term mean field essentially also comes from physics, right? So I think if you're talking about many particles, I think it's definitely possible to bring in this mean field approximation there. Yeah, but I have to look into the more detailed application.
Maybe we can I can write about the problem later on. Chat about it if you have.
Sure. Yeah. No problem. Yeah.
Thank you.
Okay, so it's almost about hour. Any other questions?
Actually, yes. Are the slides provided somewhere?
Yeah, we have recorded it.
Share.
Yeah. Okay.
What can I find?
Maybe Niao, you can send the slides to me and then I can share with people. Yeah. Okay.
Sure. Yeah, I'll do it afterwards. Yeah.
Okay. Thanks a lot. Let's thank speaker again for fantastic talk. Thanks a lot, Niao, for joining.
Thank you for hosting me. Yeah. I hope to catch up with you in person next time. Yeah.
Yeah, looking forward to it. Thank you.
Thank you. Bye-bye.
Bye.